you, the quality of my, after uploading it to Google Drive was terrible. Like, you couldn't read the word. So, I didn't do that. Did you want to send you another way?
If you guys want on YouTube, I don't care. I mean,
Well, after this week, we probably won't watch it, so.
yeah, and I did get a good, I think I got over an hour of it, so gotta get it out.
Yeah, I got half an hour.
Yeah, that out. Okay, so functions. Get this for a bit. Functions. They're going to be a huge part of this class from here on out. One of those things that once they come, they never go away. So, what is a function? You already have some, I don't know, elementary school notion of what a function is. What's a function?
You have been pretty good output.
You have an input, and it gives you an output, right? That's kind of what you've been told, and there was something special that went along with that input and that output. Every unique input has a unique output. You were probably told something to that extent.
Well, can't sometimes the output be the same?
Yeah, you can get the same output for two different inputs,
Yeah.
but I can't have the same input give you two different outputs.
Right.
That was the notion of a function that you should be somewhat familiar with. So now let's give a real definition of what a function is instead of just this intuition. Alright, so a function is a special type of relation. You remember what a relation is?
Yeah. Or a set of ordered pairs.
Set of ordered pairs, perfect. So a relation F is called a function provided that if I have AB in F and AC in F, B is equal to C. So in other words, if A maps to one thing and A maps to another thing, those things that A map to better really be the same thing or it's not a function. That's the definition your book uses. Here's the way I like to think about a function. If x is equal to y, f of x better equal f of y. And then the contrapositive is sometimes a useful way to think about it. So here's the contrapositive. If f of x is not equal to f of y, then x better not be equal to y. So these are both logically equivalent. This is how I think about a function. This is how your book says to think about a function. They're all saying the same thing. It follows that exact intuition that you have. Every unique input goes to a unique output. No input has two outputs.
Right.
If you have different outputs, you have different inputs. If you have the same input, you have the same output. Good? Alright. Let's look at some examples. And talk about some notation. So first off, here's F. F, set of ordered pairs. Is it a function?
Yeah.
Does every left-hand value go to only one right-hand value?
Yeah.
1 only goes to 2, 2 only goes to 3, 3 only goes to 1, 4 only goes to 7. Okay, we're good. And then we have this notation. F of 1. What is F of 1? When we write F of 1, we mean what's on the right-hand side of 1. Or what was 1 mapped to? 1 was mapped to 2. So F of 1 in this case is 2. You follow that? That's what the notation means. So what's F of 2?
3.
3. What's F of 3?
1.
1. What's F of 4?
7.
7. Perfect. What's G of 4? 7. What's G of 1?
2 and 3.
Ah, problem. See how we can't do G of 1? It doesn't make sense. What is G of 1? It's not defined. It's not well defined. Is it 2 or is it 3?
It's either or.
What do you mean it's either or? Sometimes we pick 2, sometimes we pick 3. Do we pick a die, roll the die, if it comes up an even number, pick the 2? Doesn't make sense. This notation doesn't make sense because this isn't a function.
Okay.
Because 1 goes to 2 and 1 goes to 3. Not a function. That doesn't work. Make sense? So F's the function, G's not a function. One of the ways you can check to see if it's a function, make sure that this notation makes sense for everything, every left-hand value.
Right.
Every left-hand value. If I can do f of 1, f of 2, f of 3, f of 4, if that always makes sense, it's a function. There's another, I don't know, sanity check, I guess.
Right.
Okay. So here's what that notation is saying in short. If f of a equals b, that means the ordered pair AB was an F. If f of 1 equals 2, that means 1, 2 was in f. If g of 4 equals 7, that means 4, 7 was in g. That's what this notation means in general. Good? Okay. Now let's look at some functions that you've already been familiar with and some shorthand that you've already been familiar with. You've seen shorthand like this to represent a function. How the heck does this represent a function? If a function is a set of ordered pairs with all these properties, how is this a function?
No idea.
So let's go over them.
Kidding, it's all squares.
So f of x equals x squared, and we'll do it on the integers. You know what I mean by on the integers?
Yeah.
We're just plugging in the integers for x. This is shorthand then for representing this relation. Negative 2 goes to 4, negative 1 goes to 1, 0 goes to 0, 1 goes to 1, 2 goes to 4.
It's like writing out the definition and not the
3 goes to 9.
Okay, wait, what? Oh, okay.
This is shorthand for this function.
Okay.
Just to save us from writing this. Here's another way to write the same function. It's a set of all x, y, where x is an integer and y is x squared.
Yeah.
This, and this are all writing the same function. So this is just a shorthand that you've come across and it's real convenient to use. But understand what this represents. It represents an infinite set of ordered pairs.
Right.
Does that make sense?
Yeah.
Wonderful. Okay, another definition. The domain and the image of a function. It's pretty simple. The domain of a function is all the left-hand values. The image of a function is all the right-hand values. So, let's go over the definition exactly. Given a function f, the set of all left-hand elements is the domain, and we represent it dom of f. And the set of all right-hand elements is the image. We represent it in of f. So, let's do an example. Here's a function. Well, first off, is this really a function? F.
Yes, it is.
1 only goes to one thing, 2 only goes to one thing, square only goes to one thing, 5 only goes to one thing, star only goes to one thing. We're good. It's a function. So what's the domain of it? The domain of f is all the left-hand values. It's 1, 2, square, 5, and star. The image of f is all the right-hand values. 2, 3, triangle, 9, and 17. So that's what we mean by that, and that's what we mean by that.
Why do we call it the image when we've heard it called the range?
Range.
Like, so why?
I know.
Why?
Yeah, multiple
Range and
names
image
for the
is the
same
same
thing.
thing.
Just because.
Because they like to confuse our little brains.
It's the English language. You have multiple words for the same thing. I don't know where range comes from. I don't know where that started being a thing.
Was the image there before range?
I don't know. I know that the only time I heard range was when I was like in elementary school or junior high
I
in
know.
algebra. From there on out, as I got into higher maths, it was always the image.
So there's even in the college algebra class, it's range.
So, yep, I don't know why we have multiple words for the same thing, but we do. So we're going to call it the image. Alright. So, another example. So we have, we already did this example. F is a set of all ordered pairs where the right-hand side is a square of the left-hand side. Right? Same thing we wrote down here. What's the domain of this thing?
Oh, the integer.
Every integer, right? And then the image of this thing is going to be all perfect squares. Right? 0 squared 1, or 0, 1, 4, 9, 16, etc.
Right.
Okay. Another definition. Let f be a function and let a and b be sets. We say that f is a function from a to b, provided that the domain of f is equal to a, and the image of f is a subset of b. And here's how we write it. F is a function from a to b. Here's an example of why you don't go around using that for such that all over the place. Because in different contexts it means different things. So f is a function from a to b is how you read that. And what does that mean? That means the domain of f is all of A, and the image of f is a subset of B.
So the function is spread out through A and B.
So f, if I were to take all its left-hand values, I would get A.
Okay.
If I were to take all its right-hand values, I would get a subset of B.
Right.
Maybe all of B, maybe only one element of B.
Subset B.
Yeah, a subset of B, not B itself.
So B.
I could get B, I could get something that's a subset of B. So we'll see examples of when these things happen. So let's look at one that you're familiar with. Let's look at the function from the real numbers to the real numbers, captured by the absolute value. You know the absolute value function, right? You don't know absolute value?
Yeah.
What's the absolute value of negative 3?
3.
3. What values can I plug into the absolute value function? Any real number.
Yeah.
There's no number that you don't know how to take the absolute value of.
Okay.
What's everything that comes out? Anything from 0 to infinity.
Right.
Only the positives. So it is a function from the real numbers to the real numbers. You can plug in any real number, and everything that you get out is a real number. But the image is just from 0 to infinity. Right?
Makes sense.
So f is a function from R to R. Let's look at another one that you're familiar with. The x squared function. So let's view it once again as a function from the real numbers to the real numbers, where g of x equals x squared. Once again, we can plug in any number we want. The domain of g is all real numbers, but the image of g is 0 to infinity. We can't get a negative number out of there. What's negative 1 squared? See it?
So if it's not 0 to infinity, not all numbers, not all positive numbers are squares.
Yeah, they are. Give me a positive number.
3.
3. The square root of 3, when you square it, gives you 3. The square root of 3 is a number. We're doing reals to reals now, not integers.
Oh.
Over here, I was saying when we're using just integers.
Okay.
So there's a leap there. So now we're doing reals to reals.
Okay.
Good? So once again, the domain of G is all real numbers, but the image of G is 0 to infinity. And then one more. We'll make h a function from the reals to the reals, where h equals a sine of whatever you plug in. Have you come across a sine function before? And sine can output negative 1 to 1. It can't output a number bigger than 1, and it can't output a number smaller than negative 1. So the domain of h is all real numbers. You can plug any real number into the sine function, but the image of h is just negative 1 to 1.
Oh, right.
Negative 1 and 1.
No, you can get anything in between.
Oh, okay. Okay.
For example, the sine of 0 is 0.
Right.
Okay, so feel like you're getting comfortable with what
Yes.
we mean by a function from A to B, and what the domain and the image are.
So B can be basically any set as long as it has
At least
all the elements of
one
A.
thing, right?
Not all the elements of A. No, A and B don't have to be related at all. They just happen to be in those cases.
Okay. If it's a function though, don't they have to be?
No,
A function from A to B.
I can make a function from the real numbers to the integers.
Okay.
And I can call it the rounding function, where it just rounds to the closest integer. Right? That could be a function.
Okay.
I can make a function from the set containing 1 to the set containing 2, where it maps 1 to 2.
And
And 1 and 2 are
Right?
with each other.
If you look at this function, so I'll say that f is a function from the set containing 1 to the set containing 2, where f equals 1, 2.
okay.
There's a really simple example.
That makes a little more sense.
Good? Alright, let's continue looking at some examples and show ways that we like to draw functions to help us make sense of them. So let A be this set, 1 through 6, and B be the set 1 through 5. And we'll make f a function from A to B, given by this. 1 goes to 2, 2 goes to 1, 3 goes to 3, 4 goes to 4, 5 goes to 5, 6 goes to 2. First off, is that a function?
Yeah.
You sure? I thought there was something in there I needed to fix.
Well, 2 can map to the same thing, but this one thing can't map to 2 different things.
So you think it's good?
2 and 6 can map to 2.
Oh no.
1 and 6.
1 and 6.
1 and 6 can both map to 2.
No, they cannot.
Okay, this is a perfectly valid function. What's f of 1? 2. What's f of 2? 1. What's f of 3? 3. What's f of 4? 4. What's f of 5? 5. What's f of 6?
Right.
2.
Okay.
So all that makes sense.
Left hand.
Every left-hand element.
Right, because so 2 can map to the same one.
2 can map to something. 3. I could have 1 goes to 1, 2 goes to 1, 3 goes to 1, 4 goes to 1, 5 goes to 1, 6 goes to 1, and it's still function.
Right, okay.
Okay. So yes, f is a function. Here's f. And here's how we represent pictorially. Here's a set A, here's a set B. F is a function from A to B. There it is drawn out. Now let's look at G. G,
No
1, 3, 2, 1, 2, 4, 3, 2, 4, 4, 5, 5. Here it is drawn out. And you're saying it's not a function, why not?
2 goes to 1, 2 goes to 4. No.
Perfect. So it's probably because 2 is going to 2 different things.
Right.
That's one problem. So now let's fix that. Let's say that we just get rid of 2 goes to 1. So we get rid of 2 goes to 1. Now is it a function from A to B?
Yeah.
So now we know 2 goes to 4. But no, it's still not a function from A to B. What's the domain of G?
1, 2, 3, 4, 5.
The domain of G is not A. 6 doesn't go to anything. So G is a function. It is not a function from A to B.
Hey, wait. What?
Let f be a function and let A and B blah blah blah. We say that f is a function from A to B provided the domain of f equals A and the image of f equals B, right? What is the domain of G?
Oh, I see.
1, 2, 3, 4, 5. Not 1, 2, 3, 4, 5, 6. So G is a function. It is not a function from A to B because it doesn't map 6 to anything. What's G of 6? Doesn't make sense. So G was bad for 2 reasons. It mapped 2 to 2 different things, and it didn't map 6 to anything. So now it's a function, but it's not a function from A to B. Okay. Let's see. Proof now. So now we have a standard type of question. The question is, so I'm looking at this set A and this set B. Forget the function for a second. I'm just looking at A and B. A natural question is, how many functions could I make from A to B?
So many.
So many. How many exactly though?
Like, will it take, like, what, 60 times or something?
Well, no. We'll look at it up.
B to the
So,
power
Oh,
of
no, that's
Ah.
Oh, yeah.
Someone to read.
A. Got him.
If A and B are set such that the size of A equals A and the size of B equals B, then there are B to the A possible functions of the form f from A to B.
Okay.
Okay? So let's make sense of this. So let f be a function from A to B, and without loss of generality, let A be this set and B be this set. We're just making this A some set that we know has A elements, and B some set that we know has B elements. Okay?
That's what you mean without loss of generality.
Yeah, I mean, A could have really been star, triangle, heptagon, whatever, but we could just replace it with something that has the same number of elements. And it doesn't change our proof. Does that not make sense? So, here's another way.
G doesn't have G number of elements, you know? It doesn't make sense.
Okay, so I have A and B. Maybe A is a set square triangle. And I'm saying without loss of generality, I can replace A with the numbers 1, 2, and it doesn't change anything.
Okay.
Because the number of functions I can make from this is the same as the number of functions I can make from this.
Okay.
That's what I mean. So whatever A and B are, just replace them with these sets that have the same size that A had and the same size that B had. You with me? Okay. Then F is of the form 1 has to go to something, 2 has to go to something, 3 has to go to something, A has to go to something, right? F has to use everything in the domain. It has to map every single thing to something to be a function from A to B, right? So now how many ways can we fill this in? How many options do I have for what I can put there? I have B options. Everything, every left-hand element comes from A. That's in A, that's in B. That's in A, that's in B.
Right. Wait, what? Oh, yeah,
Right?
right.
So here I write out all the elements in A. 1, 2, 3, all the way up to A.
Right.
And for each one of those, I need to pair it with something in B. How many options do I have?
B options.
B options.
B options. I can pick anything out of B and put it there. So I have B options for that one, B options for that one, B options for that one, B options for that one.
Okay.
So I have B times B times B times B, A times ways I can fill that out. B to the A.
Huh.
And that's what we're saying there.
Interesting.
That makes sense?
Yeah.
Intuitive sense? Alright, let's do an example in case for some reason it didn't make sense. Let A equal to set 1, 2, 3, B equal to set 4, 5. How many functions can we make from A to B?
2 to the power 3, or 8.
2 to the power 3 or 3 to the power 2?
2 to the power 3.
Yes. 2 to the 3, good. Because we are going to have 1, 2, and 3, and then we need to fill out with 4s and 5s after that. We can do all 4s, we can do 2 4s and a 5, etc. There's all 8 possibilities. Okay. Now let's talk about the inverse of a function. Now we already knew how to take the inverse of a relation. Right?
Oh, did we?
We did.
You switch them, right?
You just swap them all. You go to each element and you swap their positions.
Right, okay.
That's what it means to have an inverse relation. Same thing with a function. If I want an inverse function, I take the function, I swap all those things. But it's only a function if after all the swapping, I'm left with the function. So let's make sense of it, and then I'll say that again. So let's do A equals the set 0 through 4, B equals the set 5 through 9, and let F be a function from A to B where F has this mapping. 0 goes to 5, 1 goes to 7, 2 goes to 8, 3 goes to 9, 4 goes to 7. Right? So there's F, here's a picture of F. Now let's take its inverse. We swap all the elements. Here's what it looks like.
Same thing.
Not the same thing.
Swap. All the arrows are the opposite way.
Oh.
Instead of 0 to 5, we now have 5 to 0.
Wait, what? Oh, okay.
Right?
Arrows
We
aren't
don't have
arrows.
0, 5. We have 5, 0.
They're switched.
Oh, okay.
Can you not see my arrows? Sorry.
I can't, gosh.
This is pointing that way. This is pointing that way.
Right, so they're pointing the same way.
They're pointing the same direction, but this is A, this is B, this is B, this is A.
Yeah.
Alright, so question. Is F inverse a function from B to A?
No.
Yes.
It's got to be, right? F was a function from A to B. So F inverse has to be a function from B to A, right?
Yes.
No!
What?
It's not using 6.
Oh.
It also has 7 maps to 2 things.
And it also has 7 mapped to 2 things.
Oh.
So lots of problems. So over here, we have 4 goes to 7, 1 goes to 7. That's fine. And we didn't use up all of
Makes
B.
so much sense.
That's fine. This is still a function from A to B.
Okay.
But just because you go and take its inverse, doesn't mean you now have a function from B to A.
Right.
F inverse is not a function from B to A. First off, it's not a function. Second off, it's not from B to A. 2 problems. You understand that?
Sometimes it would work.
Sometimes it would work. So now the question becomes, what properties does it have to work?
It has to be a one-to-one function.
A one-to-one. That's exactly the next definition that we're going to introduce.
Hey, I'm gonna write 2.
Good job. Okay. So a function f is one-to-one provided that whenever xb and yb are in the function, then x equals y. In other words, if two things go to the same output, then those things were actually equal. I don't like that way of thinking about it. Here's how I like to think about it. If f of x equals f of y, then x equals y. Or, the contrapositive, if x doesn't equal y, f of x doesn't equal f of y. The reason I like thinking about it this way is because then you can see very clearly, and Estonia's already picking up on it, this is the converse of the definition of a function. You take the converse of this, and you get that.
Can you remind us what a converse is?
If alpha implies beta, its converse is beta implies alpha.
Okay.
So this implies this, the converse of that is this implies this. So if this implies this and this implies this, you have a one-to-one function. This gives you a function, the other way gives you a one-to-one function. Or this gives you a function, the other way gives you a one-to-one function. So one-to-one is the converse of the definition of a function. You see that? Okay.
This is
No.
something we've actually learned before.
I don't see it. I'm confused. What is that even saying? What's the definition of that? What is the definition saying?
If
What
you
is the
have,
definition of?
so this is what means for a function to be one-to-one.
Okay, why do we need to know one-to-one? What's one-to-one?
That's what I can explain.
What is a one-to-one function?
It's this right here. So
That's the definition of it, great. But like, what is it? Stop laughing.
Let's
You
start
laugh
with-
when you laugh.
let's start with why certain functions aren't functions. Maybe that'll help. So this function is not one-to-one.
Okay.
Because 1 goes to 7 and 4 goes to 7. That's why it's not one-to-one.
So therefore, 1 and 4.
So if we have two of the same right-hand values, 7, then the things that map to those right-hand values better be the same.
What do you mean?
They're
Give
not.
me an example of that. Of a one-to-one function.
If I get rid of 4, 7, this is now 1-to-1. Here's a simple example of 1-to-1.
Oh, okay. Yeah, that
F
makes
of
sense.
x equals x.
Okay, no, it makes sense. No more explaining.
No more explaining. Well,
It makes sense.
here's what's important for you to wrap your head around. This. Because when you're going to prove that something is one-to-one, you need to be able to think about it like this. Same with when you're going to prove that something's a function, you need to be able to think about it like this. You need to show, in order to show something's a function, you need to show anytime x equals y, f of x equals f of y. To show that a function is one-to-one, you need to show that anytime f of x equals f of y, x equals y.
Okay, hang on. So how do you know that f of x equals f of y?
How do you know that?
Yeah.
You don't know it. You assume it. You assume that this is true and show that implies this is true.
What?
Look, if I want to show that an even plus an even isn't even, how do I do it?
Okay, but
I assume x and y are even
right,
and prove that
okay,
these are
that's
some being
too
even.
complicated right now. But like, just give me a function
That
that f of x equals f of y.
They're the same thing.
so I can prove to you a function is one-to-one real quick.
Okay,
So-
hang on. Are you saying
Look,
like 5, 5?
I'll prove one-to-one real quick. Let's say f of x equals x plus 3. Okay? I'll prove that's 1-to-1. I assume, or let, I'll do assume x plus 3 is equal to y plus 3. Then x is equal to y.
Well, that's dumb.
So, anytime this is true, this is true. Anytime f of x is equal to f of y, then x is equal to y. That's how you prove it's 1-to-1.
So assume it's true, therefore it's true.
Assume this is true, therefore this is true. Assume x and y are even, therefore x plus y is even. Anytime you prove an implication, it's like you're given. Given that f of x equals f of y, show that x equals y. Given that f of x equals f of y, maybe I wrote this bad. Let me try writing it one more way to see if this clicks anything. So, proof f of x equal to x plus 3 is 1 to 1. Okay. 1. Assume f of x equals f of y. And I need to show that that leads to x equaling y.
Right, equaling.
What?
I don't know why that was so funny. What is
Then
f of y? We don't know.
you plug y into the function. Is what's confusing you that I'm using f of x here and here? Okay, let's do it this way. If f of a equals f of b, then a equals b. How's that? These are just variables.
Right.
What's f of a? If f of x equals x plus 3, what's f of a?
No idea.
What's f of 2?
What?
If f of x
Oh.
equals x plus 3, what's f of 2?
A plus 3, that's 3, okay. Fine.
A plus 3. Right?
Yeah.
Okay, so then
I see now.
a plus 3 is equal to b plus 3,
Okay.
which gives us that a equals b. Therefore, it's 1 to 1.
I'm such a dummy sometimes. Okay, I get it. Cool.
Okay, you get it, cool. So that's what we mean by 1 to 1. Anytime we get the same right-hand value, we have to have the same left-hand value. In order for it to be a function, anytime we have the same left-hand value, we have to get the same right-hand value.
This is just too general right now, but okay.
And it's wonderful. It's supposed to be nice and abstract.
That's not easy to understand though.
If it was easy to understand, what's the point of doing it? Not learning anything.
You know, I've never learned about functions.
I know, it's tragic how quickly you skip over these math classes.
Yeah.
You never really understand what they are.
We did a really good job going over and call it out for us, so that really helped.
That's good.
That's good.
Alright. A function f, let f be a function, then the inverse relation is a function if and only if it's 1 to 1. Okay, let's prove that. Let f be a function. Then f is 1 to 1 if and only if its inverse relation is a function. You understand what we're proving? So I've got a function. If its inverse is also a function, then the function was 1 to 1. Or I've got a function. If the function is 1 to 1, then its inverse is also a function. They're logically equivalent. That's what we're proving. Does that make sense?
Is that the definition of it?
No, this is a proof that we're doing.
F is 1 to 1 if and only if.
F inverse is a function. So if I know that f is a function, then f is a 1 to 1 function if and only if its inverse is a function. So in other words, we're saying.
Oh, duh, right.
Okay, great. So, I don't know, which way do you want to prove it first? If it's 1 to 1, then its inverse is a function?
Yes.
So we'll prove it this way first. 1. Let f be a 1 to 1, that's how I'm going to start doing Okay, how do we prove that f inverse is a function?
Show that thing right there, boom.
Well, what does it mean for it to be a function?
Oh, hang on. It's gonna be one of those things, like, for all x is y.
I need anytime x is equal to y implies f inverse of x is equal to f inverse of y. Maybe this is hard to think about with inverses.
It's okay, you got it.
Do you have that?
Yes, that makes perfect sense.
So if anytime this is true, then f inverse is a function.
Right.
Okay? So
So you give me
let f be a one-to-one function
such that
let's see, how am I going to get, I need two x's and y's. And let x, y in the domain of f. Pick two elements. Good? 2. Is that how I want to do it?
yes, that looks right.
I'm going to need equals. Let x, y in there, where x is equal to y. That's where this takes me. 2. Then f of x is equal to f of y. Now I need to start by grabbing two things in the domain of f inverse. Sorry, I'm thinking about this weird. Let f be a one-to-one function. And let, is that going to confuse you?
Yes, it's already confusing.
I'm going back and forth between the domain and the range, and I'm trying to think about letters to use that aren't going to confuse you.
A, B.
Let A and B in the domain of f inverse such that A equals B. Okay, so I need to show that anytime A equals B in the domain of f inverse, then f inverse of A equals f inverse of B.
A.
Okay? 2. Since A, B in the domain of f inverse,
Then f inverse of A equals f
then
inverse of
there
B.
exists, is this going to get out of hand if I do C and D?
No.
Yeah.
I think we're okay.
C and D such that
What are you doing? Come on. I feel like it's way more simple than that.
I feel like it should be pretty simple.
well,
If
should
we
see
know
what they
that they're
offer?
in the domain,
Doing.
oh, they don't equal each other.
Oh, he leaves us as a homework round already.
Oh, nice.
Alright, so let's make sense of this. Let f be a one-to-one function, and let A be in the domain of f inverse such that A equals B. Ultimately, where am I trying to get? I'm trying to get that f inverse of A equals f inverse of B. Right?
Yes, ma'am.
But if A is in the domain of f inverse, then that means something in f mapped to it. So then there exists C and D such that f of C equals A and f of D equals B. This is what I was going to say, I was afraid of.
Okay, yeah, that makes sense.
That makes good sense to you?
Yeah. And then you're gonna say C
Alright.
and D equal each other.
3.
A and B equal each other.
Since f is one-to-one, then Oh, sorry.
C equals B? Right, yeah, C and D are in it.
Let's see. F is 1 to 1. What does that mean? That means anytime its outputs are equal, its inputs are equal.
So we need to make those outputs equal.
So
So say
A is
C
an
equals
output
D.
and B is an output.
And you need,
So A and B equal implies C and D are equal.
but then you,
No,
so
no,
then
no.
you would need to write down what the inverse of that is and then show that they're equal, right?
Well,
It
let me
says
just write it.
C and D are equal, then A and B are equal.
No, I know that A and B are equal.
No, we don't.
A is what C maps to.
We don't. Oh.
B is what D maps to.
Right.
So these are the outputs.
Mm-hmm.
Since their outputs are equal, then their inputs are equal. So since F is 1 to 1,
Right.
then A equal to B implies C is equal to D.
Therefore, F inverse is a function.
Right.
There's a
For
one.
then
Right?
F inverse of A. What is F inverse of A?
F inverse of B
Is equal to B, is equal to D, is equal to, oh, not B, sorry. C is equal to D, is equal to F inverse of B.
Oh.
How do you know C is equal to D?
Yeah.
Because F is 1 to 1. Since F is 1 to 1, since the outputs are equal, the inputs are equal.
Oh, okay.
Right? I could have replaced that. Since F of C is
Oh,
equal to F of D, C equals D.
Right, those are all the same.
Sorry, I probably could have done this without 4 variables, with just 2.
Probably.
Okay.
But I've seen you through it as I was doing it.
Looks great.
So does that all make sense?
Yeah.
Yeah.
Now let's do it the other way.
Okay.
So now, what are we assuming?
We're assuming F of 1.
So
Let F be a function where F inverse is a function.
We have like 10 minutes.
Oh, yeah. Maybe you guys will just have to finish out there.
we got 10 minutes. It should
There's
be
a homework
fine.
problem.
Yeah, we have 10 minutes. 10 more minutes.
Wait,
Yeah, let's keep going.
should it be? Oh, your grid math 1 to 1. So, okay.
Yeah. Alright, you guys will have to finish that on your own.
Wait, you said let's keep going.
We have.
Well, I mean, let's keep moving forward with new material.
There's more material.
Yeah.
What?
We haven't talked about on-to functions yet.
Jeez.
Wait, what the heck?
What do we?
Why did that freaking test take so long?
Had a lot of proofs.
Bruce, take a look at it.
Alright. Onto. Alright, a function's onto if every one of the elements in B gets used. Okay? So remember, I said if we have F is from A to B, what did that mean? That means 3 things. F is a function, which tells you some information about it. That tells you that the domain of F is equal to A, and that tells you that the image of F is equal, or is a subset of B. Okay? If I say that F is onto, then that means that the image of F is actually equal to B, not just a subset.
Perfect, that makes sense.
Okay? So, f of x equal to x squared, not onto. We don't use the negative numbers. F of x equal to x cubed is onto. We use every number in the output. Not onto is onto. Make sense?
Not quite.
Not quite?
X cubed, we don't use all the numbers.
Okay, let's just do x if it's the cube that's wrong now.
Thanks, appreciate it.
Okay. I can get any number as an output. I can't get any number as an output. I can't get -2. I can't square something and get -2. Not onto, is onto. Onto just means you use up the entire codomain, the entire set B. This function is onto because we used all of B. If I now add 6 to B, it is no longer onto. Good? So that's what we mean by an onto function. It's a pretty simple idea. And then we have an idea of what's called a bijection. A bijection is a function that's one-to-one and onto. So you got a function. It can have two properties. It can be one-to-one and it can be onto. And then if it's both those, we call it a bijection. Okay? And then there's one last thing that you need to understand. If f is a function from a to b, and f is a bijection, so it's one-to-one and onto, then f inverse is a function from b to a. That's when it's safe to take its inverse and get this. You need to be both one-to-one and onto. So if you have a function from a to b that's a bijection, then when you take its inverse, you're left with a function from b to a. That make sense? That's a bijection, blah, 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 blah. And then one more thing that a bijection enables us to do is determine if two sets are the same size. So if I have f from a to b and it's a bijection, that means that the size of a is equal to the size of b, if they're not both infinite.
Then they're both infinite and they're the same size.
Kind of, yeah. They have the same cardinality is what we say.
Okay, so crap. Next. Get that.
Let a and b be finite sets with a, that. Well, that covers all the definitions. So now just looking for whatever might be the most interesting to prove. With a couple minutes left. Alright, we'll just call it there, and then obviously if you have questions next time,
Okay.
we'll go over whatever the questions are. But those are all the big ideas. So the idea of what is a function. A function means if two inputs are equal, what they map to are equal. Right?
Yeah.
That was a function. One-to-one was f of x equals f of y implies x equals y. We had onto if we had a function from a to b, then this function was onto when the image of f was equal to b. And then a bijection means it has both those properties. And those are the big ideas with functions.
Wait, one-to-one?
What's this
Here's one-to-one.
thing that
Alright,
says
what
like
does
digital
one-to-one
principle?
mean again?
So a function,
Yeah, no,
unique inputs go to unique outputs. One-to-one, unique outputs come from unique inputs. Every input only has one output. Every output only has one input. Bijection means every output has one and only one.
They're the same thing.
No. So when I have a function here, it's still a function as long as I don't have two arrows coming out of the same thing. If I have another arrow from 2 to 3, not a function anymore. Get rid of that, okay, we're still a function. But we're not a one-to-one function because I have two arrows going to the same thing. So 2 arrows going to the same thing means it's not one-to-one. two arrows coming from the same thing means it's not a function.
Okay.
That makes sense? And then 1 to 1 means we use up this whole thing.
Wait, it can't be a.
Or not 1 to 1, but on 2.
It can be 1 to 1 and not be a function.
No. That's a property of a function.
Okay.
On 2 is also a property
Makes
of a
perfect
function.
sense. Perfect.
Okay. Think we're good?
Yeah.
Yeah.
Thanks, sir.
Alright, good luck.
We only have 3 problems, so.
I'm too easy on you.